For this video, we're going to look at projectile motion concepts and do some calculations using our newly derived kinematic equations, which you can find in the previous video. So the first thing we're going to do is analyze the shape of a projectile that is going to be launched and land on level ground. So something like this. Now notice the shape that I've just drawn is a parabola, and if you remember from your Algebra 2 courses, a parabola with a vertex on the y-axis is symmetric about the y-axis. So say this was the x-axis on a coordinate plane, and the y-axis were to be drawn here, then this parabola is symmetric. And the same idea applies here with speed. Alright, so here's going to be our axis of symmetry. And that crosses directly at the top center point, where you would have a horizontal tangent line. So at this point, let's say we have a speed a for our projectile. You know, maybe it's a ball, could be really anything. And we're going to have a speed a also directly right here. Now let's say we have a speed b right here. Draw a horizontal line and you will have a speed b right here. Now that follows for maybe this point C up here and any point in between. They all have a corresponding point across this center axis. Now velocity, however, is a little bit different. So let's call up our positive direction, right? So at this point A, this projectile is going to have a velocity up. However, this corresponding point A is going to have the negative of that velocity because it's moving down, right? And notice that the lines for the velocity, these little arrows I'm drawing, they get smaller and smaller as you approach the top, where this point is. So what happens there? Think about throwing a ball in the air. It leaves your hand with a very fast speed, and by the time it reaches this top point that I marked, it has 0 velocity and 0 speed. So think about throwing that ball. When it first leaves your hand, it's going to be moving with velocity in the upward direction, right? And we're saying this ball is staying on the surface of the earth. It's not going in outer space like a rocket. It's not going to go into the upper layers of the atmosphere. It's just throwing up a ball, right? So its velocity is upward, and acceleration, it's constant, and it's always pointing to the surface of the earth, right? And that follows for every point here. Acceleration has the same magnitude in the same direction at all these points. Even up here where its velocity and speed are 0, there's still that downward acceleration. Same magnitude, same direction. Now, back here where velocity and acceleration are in the opposite direction, that means the ball you just threw is going to be slowing down. Right? And it's going to slow down until it reaches this top center point where its velocity and speed become 0, but the gravitational field, your acceleration due to gravity, it's still there. It still has the same magnitude as points A, B, and C. So after it reaches that point, the velocity and the acceleration are now in the same direction, and that means the ball that you just threw is going to be speeding up on its journey back down. Now, let's say you threw this ball off of a cliff. How would that symmetry apply here? Well, the ball will follow the parabola that I drew on the screen with the quantities we just described, right? So it's going to follow the same idea of this symmetry through the height it was launched. So once it passes this point, and that's the point that you threw it where it left your hand, then that symmetry, it's not really going to apply here, right? So points A, B, C, and every point in between will have like their corresponding matching speeds with velocities in the opposite directions of the same magnitude. So just remember, if you're launching the ball off a cliff, that symmetry will still apply until it passes the point where it left your hand. Let's go over what we just learned. So here is a parabola with 6 points, and I want you to rank the velocities, accelerations, and speeds of each of these points within a constant gravitational field. So just note that a constant gravitational field means a constant acceleration. So we remember that if we have a constant gravitational field, then the acceleration at point A is going to equal B, C, D, E, and F. They're all going to have the same acceleration. Now, what about speeds? Well, notice these dashed lines over here indicating that points A, B, and C all have a corresponding point across this axis of symmetry, right? And that means that the speed of A equals the speed of F, which is greater than B that equals E, and that is greater than C, which equals D. Right? And if you ever forget, is C bigger or is A bigger, remember that up here we are moving at 0 meters per second, right? So that means that if we throw this projectile up, that it is slowing down as it approaches at 0 meters per second. Now, moving on to velocity. Let's call upward our positive direction, right? So that means that points A, B, and C must all have a greater velocity than D, E, and F, because all of these points have a negative velocity. And looking at these arrows, we can tell that A is moving faster than B, is moving faster than C. Now, which point is moving faster on this side? Point D, E, or F? Well, whichever one has the greater velocity is the one that has the least negative velocity. So if we were to draw arrows coming back down, you can see they're getting larger as we reach the bottom of this parabola. So that means that D has a less negative velocity than E and F. So we go D to E to F. So if you have a notebook or a piece of paper with you, this would be a good thing to write down to know how the velocity or the rankings of the velocity change as you move along this parabola. But if we were to include this point right here, it's moving at 0 meters per second, so it would go right in between C and D before this side gets negative. Alright, so this problem says that a ball is thrown into the air on Earth and is subject to free fall at an initial velocity of 20 meters per second at a height 4 meters above the ground. How long does it take the ball to return to its launch height? Part A. So let's start there. And notice that I've underlined the ball is subject to free fall. That just means that the only force acting on it is the force of gravity. So remember in the last video that I said if we have 3 out of the 5 kinematic variables, then we can solve for the rest of them. So let's start by making a chart. So we know our initial velocity is 20 meters per second, and that's going to be positive because we're calling upwards our positive direction. We haven't really clarified a final velocity. If the ball is subject to free fall on Earth, that means it has approximately an acceleration of negative 10 meters per second squared towards the center or the surface of the Earth for our purposes. The true acceleration on Earth is 9.81 meters per second squared, but on the AP exam you're going to be allowed to use 10, so we're going to use 10. We have an initial position of 4 meters above the ground, have not clarified a final position, and for part A we're looking for the time it takes the ball to return to its launch height. So let's revisit the idea of our symmetric parabola to figure out the change in time. So if all of these points have matching corresponding points of speed on the opposite side of our axis of symmetry. That means it's going to take the same amount of time for the ball to travel up as it does for the ball to travel downwards. So let's figure out part A by solving for the time it takes the ball to reach its top center point, and then multiplying it by 2, right? Because this point here is going to have the same time here as this part. So let's go ahead and do that. So we want to solve for delta t. And notice that our positions here are kind of messy. So let's use an equation that doesn't have a change in position in it. So that would be final velocity equals initial velocity plus acceleration times change in time. So let's solve this equation for delta t, and you should get final velocity minus initial velocity divided by acceleration. So if we plug in all of our variables from this chart over here, that's why it's really useful to make a chart, we would have 0 minus 20 divided by negative 10, and that will give us a time of 2 seconds for the ball to reach its maximum height above the ground, which we should use for part B. So keep in mind this 2 seconds right here. So if it takes 2 seconds for the ball to travel upwards to that maximum height, then it's going to take it 2 seconds to travel downwards and reach its launch height. So that means our delta t here is 4 seconds. Alright, so now we want to know what is the maximum height above the ground reached by the ball. Well, at that maximum height, we're going to have a final velocity of 0 meters per second. And we want to solve for this final position. So let's use this kinematic equation we derived in the last video that says final position equals initial position plus initial velocity times time plus 1/2 times acceleration times change in time squared. So luckily this equation is already solved for our final position, so we really just have to plug everything in. And that will be final position equals, our initial position above the ground is 4 meters. That's why I chose to use this equation, because it accounts for that more easily than the other ones do. Our initial velocity is 20 meters per second. Our time to reach our maximum height is going to be 2 seconds plus 1/2 times our acceleration of negative 10 meters per second squared towards the center of the earth times our change in time of 2 seconds squared. So we can simplify it. We say we've got final position equals 4 plus 40, and then we've got 1/2 times negative 10, so that's negative 5, times 2 squared is 4, so negative 5 times 4 is negative 20. And then if you add all of this together, you should get a final height of 24 meters above the ground. So it's going to take the ball 4 seconds to make a round trip back to its initial launch height, and it's going to reach a maximum height above the ground of 24 meters, and that, notice, is 4 meters above the ground from its launch height. So it's launched at a height of 4 meters, and then from there it's going to travel an additional 20 meters. And it's going to reach this maximum final height of 24 meters. So here's a challenge problem for this video. You can go ahead and read that. For part A though, I want you to think horizontally and vertically for that distance of separation. and the solution will be posted within 24 hours on my Instagram page, link in the description of this video, or you can find it at the beginning of the next video.